Welcome back to Learning from a Layman. I'm Carl Christensen. This is a new type of podcast we'll do on occasion. This is going to be a best of episode, so I'm compiling some of the highlights from a few of the physics and math based podcasts that we've done in the last 2 years, and I hope you enjoy listening. We'll start with Isaac Newton. He did come up with calculus, but let's not hold that against him. Everyone slips up and invents another branch of math occasionally. But he did do lots of good things as far as describing the way that we understand the world, the universe, motion, gravity. And so let's talk about his 3 laws of motion, which I think are kind of the first things you learn in physics, though I wouldn't know because I don't know the first thing about physics. So, Matt,
before we go too far, I will point out that Isaac Newton and the Newton family has what is possibly the most metal coat of arms of all time. It is simply a black shield with white crossbones.
Wait, is that the pirate?
Pretty close. Doesn't have the skull, but it doesn't need the skull because they're just that cool. So, yeah, as you guys mentioned, Newton is known for a number of things, and he actually contributed a huge amount to almost all the fields of physics and that branch of science. Physics encompasses a lot: motion, gravitation, all of the forces of nature, light, electromagnetic waves. He was the one that realized that you can split light with a prism and then recombine it, and that sunlight actually carries in it all the colors. A lot of people are familiar with the fact that Newton had some laws of motion, but very few people know what they are, so I will zip through those really quick if you like. I can give you kind of the layman overview without quoting directly from Wikipedia.
All right.
So the first law of motion: every body persists in its state of being at rest or of moving uniformly straight forward, except insofar as it is compelled to change its state by force impressed. Simply
that
put,
wasn't layman.
An object at rest will remain at rest, and an object in motion will remain in motion, unless another force is brought to bear on that object. So if your thing is not moving, it is not going to start moving unless you push on it. And if it is moving, it will not stop moving unless something pushes back against it. That is his first law of motion. In practice, when you think of a car, your car is moving, right? And if you take your foot off the accelerator, it will eventually come to a stop. But you need to understand that there are always forces acting against your car: friction from the road, air resistance, friction from the internal mechanics and mechanisms in your engine, and so forth. But if you imagine a car moving on a frictionless surface, or a better example, imagine that little plastic puck moving on an air hockey table. If it starts moving, it's not going to stop moving until it bumps into something. So that's Newton's first law. If your thing is not moving, nothing's going to start it moving until you apply a force to it. And if it is moving, it's going to keep going until another force stops it. Newton's second law of motion is the alteration of motion is ever proportional to the motive force impressed, and is made in the direction of the right line in which that force is impressed. And it's impressed with an apostrophe D, which is a little weird, whatever. All that says is that if your motion is going to change, it will change in proportion to the force that you put on it. If you apply a light force, you will apply a small change to motion. If you apply a large force, you will apply a large change to motion. So, if you are driving down the freeway in your car at a constant speed, not changing your acceleration, your car is in motion, and it swats right into a bug, that bug is going to apply a small force to your car, so small that it won't really be noticeable. If you apply the force of an unfortunate bird to your windshield, you'll apply a little more force, you'll hear it, it'll make a sickening thunk, but it's not going to change the motion of your car too much. If you apply a larger force in the form of a Utah mule deer to your windshield, that will cause a significant change in the motion of your car. It will cause a negative acceleration. And if you apply a larger force, like a Wyoming buffalo, to the front of your car while it is in motion, it will apply an even greater negative acceleration, and you will definitely feel that. And finally, if you apply an overwhelming force, like a brick wall, to the windshield of your car as it is in motion, then you will see a nearly instantaneous change in that object's motion or velocity. It will go from moving to not moving because the force is so much higher. That's all the second law says. Any change in motion is relative to the amount of force that you put on it. The equation that comes into play is force equals mass times acceleration.
Right. I heard about that.
Yeah, indeed. F equals
F
ma.
equals ma.
So if you're in motion and you're not changing your motion, according to Newton's first law of motion, when you're just cruising along and there's no other forces in play, then your acceleration is 0. Your velocity is whatever it is, say 60 miles an hour. But in the absence of any other force, pretend there's no friction, pretend there's no air resistance, pretend there's no mule deer, your acceleration is 0 because you're not changing your speed. So the force being applied to you is
0.
Also 0. F equals ma. 0 equals the mass of your car, say, I don't know, 3,000 kilograms, times the acceleration, which is 0. Now, if you want to change the acceleration of your car, your 3,000 kilogram car, and you want to change it by 3,000 meters per second squared, then you would need to apply a very large force. Your force would equal 3,000 kilograms times 3,000 meters per second squared would equal 9 times 10 to the 6th newtons, which is a bunch of newtons. Now, imagine instead of your 3,000 kilogram car, you have your 30 kilogram child. It's charging down the hall, and you want to bring it to an abrupt stop. You don't need to apply nearly the same amount of force, like, a fleet of mule deer to your child to stop it from running down the hall as you would to your car. So the two variables, mass, acceleration, really 3 variables, mass, acceleration, and force, they all just change on how quickly you want the acceleration to change and the mass of the object that you're starting with. A heavy mass is going to take more force to bring about a large change in acceleration than would a small mass. That has to do with inertia. Okay, the third law of motion reads, as Newton wrote it, to every action there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. So what that says is anytime that you apply a force to a thing, the thing applies a force back to you. So when you push on your car to get it moving because you've let it run out of fuel in the middle of the street and you need to get it out of the way, you push and you push and you push and the car slowly starts to move, but you do not fall through the car. You do not you cannot move through it as you would if the car was not there because the car pushes back on you. Likewise, to my knowledge, none of us have ever fallen through a solid floor.
Well, Cameron, wait, hold on. Cameron? Can we confirm?
Okay. Anyway, to my knowledge...
Yes, I have fallen through a roof.
All right.
Okay, well, that's different. Roofs are in their own branch of physics entirely.
Exactly.
So we apply a force to the floor every second because gravity is pulling down on us. We apply a force equal to the acceleration of gravity, 9.81 meters per second squared, times our mass, which for me is a svelte number of kilograms. But the reason I don't fall through the floor is because the floor pushes back on me with an equal force. That's what Newton is saying. Anytime a force is brought into play between two objects, that force is directed against both objects in opposite directions. So one of the big things with Einstein's theory of relativity that just blows people's minds, including my own, is imagine that you are on the freeway on I-15 traveling to wherever you're going. And you're going along at 95 miles an hour because you're a renegade and that's how you roll. The highway patroller that is chasing you down is closing on you, and he is traveling at 120 miles an hour. What is your relative speed to that highway patroller? If he's going 120 and you're going 95, he is closing on you at a relative speed of 25 miles an hour. Now, the highway patroller in the other lane, who is coming to intercept you, also going 120 miles an hour, is moving relative to you at a much faster speed. He's moving at 120 plus 95 miles an hour. So that's what, 220 miles an hour? Something like that? Yeah. So that's just very basic relative motion. Now, here's where you start to destroy minds. Imagine that you shine a light from your car moving at 95 miles an hour towards the back of a truck in front of you that is also moving at 95 miles an hour. The light hits that truck at the speed of light, right?
Sure.
Okay. Now, imagine that you shine a light at the highway patroller in the other lane who is moving to intercept you, who is coming towards you. Imagine at the same time that he shines a light back at you. What is the closing speed of the two beams of light? You're shining light at him, and that beam is moving at the speed of light. He's shining light at you, and that beam is moving at the speed of light. The relative closing speed of those two beams of light is?
Twice the speed of light?
It is not. It is the speed of light. So, well, before I move on, I'll mention one thing. I mentioned E equals mc squared. That is actually a consequence of the theory of relativity. And I won't go into how, but basically that equation states that energy and mass are equivalent and can change from one to the other. That doesn't sound like it should be a thing, right? You're either a thing or you're energy, not both. Well, that's true, but you can move from one to the other. In fact, when we dropped the nuclear weapons on Hiroshima and Nagasaki, the atomic weapon that we dropped on Hiroshima, part of it was so powerful. During that detonation, roughly 0.7, that's less than a sheet of paper, grams of matter were converted to energy. And that's what created that massive nuclear explosion. The fact that matter became energy in that reaction. 0.7 grams leveled that city. So that, and it does so according to that equation. Energy equals the mass of the object times c, the speed of light squared.
The laws of thermodynamics are a couple of things that the scientific community has accepted over the years, and they've been restated in different forms, but they're really important in governing our understanding of energy and what is possible with energy and energy manipulation. So there are three laws of thermodynamics that were initially accepted and understood, and then the community stepped back and realized, hey, we're missing a baseline definition here, and so they proposed a fourth law of thermodynamics. But because that fourth law was the underpinning of the other laws, it really needed to come first. And they didn't want to renumber all of the other laws, and so instead of making it the fourth law of thermodynamics, they have made it the 0th law of thermodynamics. No, I am not kidding. And
it makes
so
a lot of sense to a computer scientist. You start counting at 0 anyway. So
yes, but that's not where we want to take our baseline from. But anyway, So you have the 4 laws of thermodynamics, the 0th law, the 1st law, the 2nd law, and the 3rd law. And all of these things basically tell us how the world works in terms of heat and energy transfer. Thermodynamics being, a 2-part word, thermo, heat, and dynamics, motion, movement, transfer, change. So the laws of heat change. The 0th law is simply that if you have 2 systems and they are in thermal equilibrium with each other, or I'm sorry, with a third system, you have systems A, B, and C, and A is in thermal equilibrium with C, and B is in thermal equilibrium with C, then A and B are also in thermal equilibrium with each other. So you have 3 things. The first 2 things are the same temperature as the third thing. Therefore, the first 2 things are the same temperature. You look at that and you kind of go, well, duh. And you should. But nonetheless, that's an important law to state, because without that law in place, you cannot have such a thing as a thermometer. Because your thermometer is supposed to be a gauge of temperature, is it not? If you're using it for any other purpose, I don't want to know. But the whole thing that makes a thermometer worth doing is that your thermometer comes into thermal equilibrium with whatever thing it's touching, and that gives you a reading on a scale. If you put the thermometer next to something else, it becomes into thermal equilibrium with that thing eventually. And because it is able to reach that thermal equilibrium consistently, and because the 0th law of thermodynamics is true, that allows us to have that measurement scale and that measurement instrument. If we did not have the law, then the only way that you could scientifically prove that 2 objects were the same temperature would be to touch them together and see and wait for them to reach thermal equilibrium through their exchange of heat. That's the only way that you could prove that 2 objects were the same temperature. So it's a kind of facepalm and why do we need this thing kind of law, but is fundamental for the types of people who care about scientific proof that we have that one in place.
Okay, so speaking of proofs,
Woot.
I know relatively, well, not even relatively, I know precious little about proofs in general, but I know that physics and mathematics are complementary branches of stuff, of a thing.
That's
no?
some interesting language you're using.
Well, okay, you use mathematics and physics a lot, is I guess what I was trying to say, right?
As well as in chemistry, biology, zoology.
Well, okay, some of those you use less math. Let's just say in physics, in theoretical physics, you better have a good understanding of mathematics, right?
Shopping.
Okay.
Yes.
So proofs in math are like they're a actual, like an equation, like you have a proof, right? Like this equals this, and that is a fundamental proof, and you have to be able to mathematically take through the reasoning behind it. Is that the case with all of these laws?
Yeah, your laws of your truly accepted laws of physics have to be provable. Otherwise, it's a theorem. It's an idea. It's something that makes a lot of sense and no one has been able to disprove, but I cannot say for certainty that it is correct in every case because I cannot prove it. The laws of thermodynamics are laws because they are proven and provable. The 0th law is important because it is fundamental to the provableness, that's a word, of everything else.
Okay, and so I guess what I'm trying to underscore or question, because I'm not entirely clear, but the idea that when we talk about something being provable or proven in the area of physics or thermodynamics, we're actually talking about mathematic proof. I've done a scientific study and I've shown over this large sample size that no, it's literally I can take you through the mathematics of why this is the case, right?
Yes. Yep.
Right. So when
eventually you come to an equation that ends up saying 1 equals 1, and therefore this is true.
Right, exactly. So when you see a lot of like movies or whatever where you get physics, geniuses, savants writing equations up on the board, a lot of those they're trying to get to the point where they can do proofs for particular ideas and laws to prove theorems, right?
Right, and other things.
Okay,
Movies
sure.
are definitely the best way to learn
That's
anything.
the only way I've learned anything in life. All right.
The first law of thermodynamics, which is number 2 on the list, basically says that when you have a closed system with a certain amount of internal energy, the only way that you can change the internal energy of that system is to apply heat or work or matter or something into that system. And the change of the internal energy is equivalent to the amount of energy, work, heat, whatever chucked into it, minus the work, heat, or energy emitted by the system during that reaction. Okay, if you think about that and I restate it, it basically says that if you have energy X, you add energy Y, and you take out energy Z, your total energy is X plus Y minus Z. You look at that and you think, okay, well, that makes a lot of sense intuitively also. Why does that need to be a law? This is really just a restatement that of the law of conservation of energy, that energy cannot be created or destroyed, that when an energy reaction happens, the energy goes somewhere. It doesn't evaporate into the void. It is used. It is manifested in some form. It either leaves the system or is input to the system, and that change can be mathematically determined. An example, I have 5 buckets of energy. I chuck them into a light bulb. The light bulb emits energy in an equivalent amount. It will absorb 1 bucket of energy and re-emit it as heat. That's why when you touch a light bulb, it burns you. And then it chucks out 4 more buckets of energy as light. 1 plus 4 equals 5. That's all that it's saying. All of my buckets of energy went somewhere. Some of them went to heat. Some of them went to light. None of them evaporated into the ether. None of them were destroyed. And I did not get 6, 7, 8, 9, 10 buckets of energy out of that light bulb. I got an equivalent amount out. That is the first law of thermodynamics. The energy that you put into the system is equal to the energy that comes out of the system minus any change in the internals. One of the consequences of the first law of thermodynamics, and this is going to ruin a lot of dreams out there, I can tell, is that you absolutely cannot have a perpetual motion machine that does more work than the energy that you put into it. You can't get infinite energy out of a device, no matter how you engineer it. So, second law of thermodynamics. There's a whole bunch of ways to say this one, including a bunch of stuff about entropy, but the really basic one is that when you have some water and you put it on a blazing hot pan surface, generally you will not see an ice cube form and the pan get hotter, because the heat that is in the water does not go into that blazing hot pan. The result would be, imagine you place some water in a pan that's on the stove. Would you expect to see an ice cube form out of that water with a lit burner underneath it?
No.
No, because that would mean that the water is transferring its own heat into the already hot pan. The second law of thermodynamics says that energy transfer does not go that way. It goes the other way. You cannot transfer heat from a cold object to a hotter object. It just does not happen that way.
It kind of like akin to the law, water flows downhill.
Yep.
Right? But energy flows towards its towards neutralization.
Well, yeah, it flows from hot to cold, essentially.
Okay.
So when I have my hot pan surface and I dump water on it, what I will see is heat will transfer from the pan into the water. The pan will actually cool down. The water will heat up. And if I leave them sit there and I turn the burner off and I don't add any more energy to it, both of those items will reach a thermal equilibrium with each other somewhere in between their two starting temperatures. The pan will cool to colder than it was, and the water will heat up to hotter than it was. And then they will sit at that same temperature, whatever it is, for all eternity, unless energy is further applied to it or taken out of it. The big thing is that that energy transfer doesn't go uphill. Heat always goes from hot to cold. The third law of thermodynamics is weird, and this one matters, I think, a lot less to the layman or most people. But basically, there is a temperature called absolute zero. It is negative 273 point something degrees Celsius. Absolute zero is defined as the temperature in which there is no molecular motion, because molecular motion, which we did not talk about, is the source of heat. If there is no molecular motion, there is no heat. It is really, really cold. You cannot actually achieve absolute zero, because the third law of thermodynamics basically says that the disorder, the entropy of a system, approaches a really small constant value. If it's pure substance and it's not glass, it will be zero, as the temperature approaches zero.
So I have a question about this. How did they figure out the number, the negative 273, 0 Kelvin? How did they figure out that there would be no motion at that point if they can't reach that point?
I think that, well, I mean, it's always an approximation. It's not negative 273.15. It's negative 273.1, who knows what. But just if you're familiar with a lot with certain types of mathematical graphs of different functions, you'll see something called an asymptote. It's a value on your graph.
I don't
Watch your
appreciate that
language.
language.
Yeah, that's right.
Shut up. So the expression as y approaches 2, x approaches infinity. What that means is that if I have two values, x and y, and they're related somehow, as my y value gets larger and larger and larger and approaches 2, my x will approach infinity. Now, I can't actually get to infinity, can I?
Not that
No, I don't have that power, and neither do you.
Only
Maybe.
Buzz Lightyear can, but he
Yes.
actually goes beyond it.
Yeah,
That's right.
But what that means is that in order for Buzz Lightyear to get to 2, he actually has to get to infinity and beyond it. The rest of us mere mortals who are not space rangers will never get to 2 because we can't get our x to infinity. Likewise, you can see mathematical functions in nature that show similar asymptotes. So if I start cooling my object and I cool it and cool it and cool it, and I put infinite energy into cooling it, I can see that the temperature is approaching negative 273.15 Celsius, but it will never quite get there. That's the asymptote. That's how you determine what that value could be. Calculus is basically the study of how mathematical functions change. And there's really two parts to it. There is differential calculus, or derivative calculus, which deals with the rate of change of a thing. And then there is integral calculus, which deals with accumulations of volume or area or product or something as a result of a function. And when we say function, we're talking about an equation that relates one or more variables to another variable. The classical functions are x and y functions. If you imagine an xy grid or graph, you can have an equation that shows how x changes as y changes. The very basic function is x equals y. So when x is 1, y is 1. And when x is 2, y is 2. And if you graph that on a piece of graph paper, it's a straight line at a 45-degree angle going from the bottom left to the upper right. And that's it. That's a very, very basic function. Calculus deals with change in the lines that are represented by those functions. And it also deals with the area under that line. The change is the derivative part, and the area under the line is the integral part. The basic function that I'll want you to visualize is, imagine you have a field artillery piece, because most of us have one of those in our backyard. You crank the barrel up to about 85 degrees, so it's pretty steep. It's not vertical, but it's pretty steeply inclined. And you fire it as you do. The shell goes way, way up, and at about however many thousand feet, it levels off. It's moving away from you horizontally, and then it comes right back down and obliterates your neighbor's house a few blocks over. The arc of that cannon shot can be considered a mathematical function, and that the shape of that arc, that really tall parabola, is what we'll be talking about. So imagine you have that parabolic arc as represented by that cannon shot. Now, at any given time, because you've suddenly become fixated on understanding everything about where this shell is throughout every moment of its flight, at any given time, you can determine the position of that shell using an equation that relates its x and y coordinates. For instance, if the parabolic equation is a y equals x squared kind of function, you know that when x is 1, well, 1 squared is 1, so y is 1. When x is 2, 2 squared is 4, so y is going to be 4, and you can see that line is going to go up pretty steeply. Now go back to that cannon shot parabola. That's a mathematical function of some sort. And that function will tell you the position of your shell based on those x and y coordinates. But what if instead of the position of that shell, I want to know the direction the shell is headed at a given moment? The instant I fire my artillery piece, I know that that shell is headed out of my gun barrel at 85 degrees, right? Because that's where my gun barrel is. Yes? Somebody acknowledge.
I think that is the case.
Yes, it totally is. Okay. The instant after the shell leaves the barrel, it starts to, its trajectory alters, and its line of ascent changes. And at the top of that parabolic arc, what way is the shell pointing? It's pointing flat horizontal, isn't it? As it's right about to come back down. So throughout the flight of my little shell, I've gone from an angle of 85 degrees to an angle of 0 degrees. And now I'm going to start plummeting back towards Earth, and my angle is going to drop. If I want to understand that change in the way that my shell is pointing, that's where a derivative in calculus can come in handy. Your derivative of a mathematical function is going to give you the slope of your line at any given point. If I take the derivative of my cannon shot parabola at the top of the arc, it's going to give me a slope of 0. That's the point where the cannon shell is at the top of its arc, has leveled off, and is just about to come down to Earth. If I take the derivative of that function at the initial point, at time equals 0, I'm going to get a slope that will be equivalent to my 85-degree elevation for my gun barrel. And if I take the derivative of that function at the impact point, I'll similarly get a negative 85-degree slope. And that is what it is. That's the kind of first application of calculus here. If you want to know the slope of a line at any given point for a mathematical function, you take its derivative. And the rules for that you can find in any calculus textbook. You can look them up and play with that all day long. I don't care. But that's more or less what, this is the basic concept of what you are doing. The initial function, that parabola that you trace out, that initial mathematical function will define that parabola, and that will tell you position throughout the entire flight, and that tells you the endpoint and everything else. What it doesn't tell you is the slope of the parabola at every point. And so I'm going to shift gears here and use a different example. Another function we're going to use is the position of a car. Imagine that you are in your car, you are stopped on the street, and you start driving forward by pressing the accelerator. Now, what is your speed? It's changing. You do not go from 0 to 60 miles an hour instantaneously. You go from 0 to 1 mile an hour to 10 miles an hour to 45 to 120. And you do it over time. The other part of this is consider how you apply the accelerator. When you are at a stop and the light turns green, do you stomp the pedal to its maximally depressed position and just flood your engine with gas and blast yourself off the line like the boss that you are? Because that's what I do, but most people don't. Or do you gradually ease into it by depressing your accelerator a little bit and then a little more until you get up to speed, and then you kind of open it up and really start moving forward?
Depends on the day, but I generally go with the second one.
Yeah, most people do, because most people are actually fairly reasonable drivers. But the thing is, when you do that, you're pressing your accelerator down to a varying degree. That also means that your acceleration is not the same as you speed up. And so if you want to trace the position of your car, you have to understand that you're not dealing with a constant speed, and you're not even dealing with a constant acceleration. And if I really want to model the entire dynamics of my car moving forward, I need to know those things. Fortunately, I have calculus. If I can define a function that determines where my car is over time, then I can take the derivative of that function to determine its speed at a given instant. And with that, I can take the second derivative, I can take the derivative of that same function again, and determine the acceleration of my car at a given moment. So let's say that I accelerate from 0 to 50 miles an hour, and I do that in so many seconds. I can, if I've got the positioning of my car and I've got the function that represents that positioning as I'm zipping down the street, I can use the derivative of that function to pull out my speed at any given moment, all the way from when I started at 0 to when I hit my steady state at 50 miles an hour. I can then take the derivative of that derivative and get my acceleration all the way from when I was at 0 to when I started to press the gas pedal and I was accelerating slowly, to when I stomped the gas pedal and I was accelerating quickly, to when I let off the gas pedal again and my acceleration dropped to 0 and my speed remained constant at 50 miles an hour. That is the type of thing that differential calculus allows you to do, take a position function, take the first derivative of it to get your speed at any point there, and take the second derivative of it to get your acceleration at any point. That has a number of different applications depending on what it is that you're trying to understand and model. Going back to my cannon shot, the position of that shell in three-dimensional space, or rather in two-dimensional XY space, is represented by some function. I can determine the angle it's pointing by taking the slope of that line at any given point by taking the first derivative of that function. That's kind of some two basic examples of what you can do by taking derivative functions or derivatives of a standard position function. Let's say I only know how hard I'm going to stomp the accelerator. And I know how hard I'm going to stomp the accelerator at every moment throughout my car's little journey. Can I figure out how fast I will be going at any given point? And with that, can I figure out my position at any given instant? The answer is yes, I can. But now I'm not taking derivatives because I'm starting with a derivative. I'm starting with a second derivative. I'm starting with acceleration, and I want velocity and position. And the way that I get that is with the second half of calculus, which is the integral side. The way that you back out velocity from position is by taking the derivative. And the way that you back out acceleration from velocity is by taking another derivative. The way that if I have a function that gives me an approximation of the trajectory of my little bullet, then by taking the derivative, I will get an approximation of the angle of that bullet at a given moment. If I have a function that precisely models down to the atomic level all of the interactions that explicitly define that bullet's flight path, I would do the same calculus equation on that function, and I get a very, very precise equation, that a derivative that shows me that bullet's pointing. Integral calculus can be thought of as defining the area underneath a curve. So going back to my artillery shell carves out a beautiful arc in the sky. How much two-dimensional space is underneath that arc? Well, if I really wanted to find that out, I would take the integral of my bullet function, and it would show me that there are X many square feet of air underneath my arc. Likewise, if I have a function that tells me how many cases of coronavirus I'm getting every day, how many new cases, and I can determine the equation for that function, then I can take the integral of that function, determine the area under the curve, and that is my total number of sick people. It also goes back to your question about the acceleration of your car. I have a function that tells me precisely how my car is going to accelerate based on how I depress the gas pedal. If I have that, then I can take the integral of that function and I can get velocity or my speed. And now I've got a function that determines precisely how my car's speed or what my car's speed is at any given moment in time. Well, that's neat, but I want to know my position. So if I take the integral of my speed function, I can now get my position out of that. This kind of goes to the fundamental theorems of calculus, and well, I don't actually want to touch on that, but the basic thing is, if you have position, you can take the derivative and get speed or velocity. If you have velocity, you can take the derivative and get acceleration. If you have acceleration, you can take the integral and get velocity. And if you have velocity, you can take the integral and get position. So if I have any one of those three functions, if I have a function that gives me my position, or my function that gives me velocity, or my function that gives me acceleration, if I can do calculus on that one thing, then I can determine the other two things out of it. Give me velocity, and I can tell you position and acceleration. Give me acceleration, and I can tell you position and velocity. And it's just a matter of taking the appropriate integrals or the appropriate derivatives to find the missing functions. Our correct understanding of orbital mechanics really came about with a very smart dude named Johannes Kepler. But he is the guy that kind of defined the real true equations for orbital motion. And he, all of these scientists, they come out with their laws in groups of three. So Newton had his 3 laws of motion. Kepler had his 3 laws of orbital motion. An object is in orbit if it is able to move at a fast enough speed that essentially the ground falls away below it at the same rate that it falls toward the ground.
Okay, I might be jumping the gun here, but as you get higher away from the Earth, the rate at which you fall is going to change, right? So
very much so, yes.
So the higher you go, the less quickly you need to move in order to remain in orbit, right?
Yes, and that is a perfect segue into Kepler's laws of orbital motion. So he figured out that orbits were a thing, and he really wanted to quantify things like how fast you need to go at different altitudes, and what are the laws that govern a general shape of an orbit. Can I have an orbit that is a triangle? He quickly determined, no, you can't. But his 3 laws, and these apply to any situation where you have really only 2 objects. So, for example, the Earth and the Moon, or the Earth and a satellite, or the Sun and the Earth. Any system where you have 2 objects like that, one orbiting the other, will obey Kepler's 3 laws of orbital motion. And the first law is that your orbital shape is going to be an ellipse. Not quite a circle, but an ellipse. And that is what your satellite will move around in. Your second law is, also the central point, or the kind of reference point for that orbit, that the satellite will orbit around, is going to be at the focus point of one of those ellipses. And you can tune into our podcast, An Introduction to Geometry, which we will definitely do at some point probably, to learn more about ellipses and their focus points. But if you look at any satellite that's orbiting the Earth is at one of the focus points of that orbital ellipse. The second law is complex and talks about how, as a satellite moves around that elliptical track, if you draw a line between the satellite and the center point, the Earth or whatever it is, that line will sweep out an equal area for any equal intervals of time. Okay, that's neat sounding, but what it actually means is that the speed of the orbiting satellite varies depending on where it is in the ellipse. And what you have are 2 concepts, apogee and perigee. Apogee is the point in the ellipse that is furthest from your central point, the Earth, and perigee would be the point where a satellite is closest to the Earth. I'm just going to use the Earth satellite system. This could also be Earth Sun or Moon Earth or whatever, but I'm just going to say Earth satellite. If you think of a roller coaster, you go up the little track and you chug along, and you're not moving very quickly as you increase elevation toward that apex point. And then you're at the apex, you slowly start to tip over. You're still not moving fast, even though everyone is shrieking. And then you reach that point where you're on a downward slope, and suddenly the roller coaster is moving very, very, very quickly. And its speed is at its maximum when it hits the bottom of that, drop. And then the speed decreases as it goes back up the hill toward another peak point, and everyone catches their breath, and then the roller coaster is chugging along at low speed until it hits the next drop, and then you go down faster. Well, satellites are just like that. They're like a roller coaster. And that apogee point, where you're farthest from the Earth, is the point in the roller coaster where you're at that peak and you're not moving very quick. And it's the same with a satellite. A satellite at apogee is going to be moving at slower than at any other point in its orbit. And then as it starts to come back down towards the Earth, toward that perigee point, towards that lowest point, it's going to accelerate until when it reaches perigee, it's moving at its maximum orbital speed. That's Kepler's second law. Satellites are roller coasters. That's the best way to sum it up. Anyway, that was Kepler's second law. Kepler's third law is more of the quantification of speed as relates to the geometry of the orbit. And you actually hit this earlier. If you're at a low altitude, you need to be going much faster in order to maintain a stable orbit. If you're at a high altitude, because of the changes in gravity and the forces that are on you, you're actually moving much slower. And there is a specific equation for that. For those of you interested, it is your circular velocity is equal to the square root of a constant g times the mass of the Earth divided by the essentially the orbital radius, the distance between the satellite and the center of the Earth. That's cool. You can look up that formula. Nobody cares. But what it really means is that a satellite way clear out there in a distant orbit is going to be moving at a much slower speed than a satellite like the International Space Station that is relatively close to the Earth and is zipping along pretty quickly. The electromagnetic spectrum is just the continuum of different electromagnetic waves by their different frequency ranges. And going back to what a wave is an oscillating field, means it goes up and down, that oscillates at a given frequency. And that frequency can be 1 beat per minute, 1 beat per second, 1 beat per nanosecond. It can be anything.
Beat as defined as the gap between peaks in the wave, right?
Yep.
Or trough, wherever you're measuring.
Yeah, exactly. And your wave has that, well, it has that wave shape with a peak and then descending down to a trough and rising to another peak. And it does that at a regular interval forever. And that is the interval between those peaks or between those troughs or whatever is the frequency of that wave. The electromagnetic spectrum is made up of every wave you can imagine that is an electromagnetic wave at every frequency, starting with extremely low frequency waves that go between peaks and troughs at about 1 to 3 cycles per second, all the way up to incredibly high frequency gamma rays that have frequencies that are in the 300 exahertz range. Exahertz meaning that you have 10 times 10 to the 18th power cycles per second.
Wow.
And when we say hertz, it's Hertz. 1 hertz is 1 cycle per second. So 3 hertz, 3 cycles per second. 300 exahertz, 300 times 10 to the 18th cycles per second. It's a bunch. It is a large number.
As they say, it hurts a lot.
Nobody says that.
No.
Blimey.
Anyway, so when we talk about electromagnetic waves, what we're talking about is that peak-trough oscillation of an electromagnetic field. And when we say electromagnetic field, we mean an electric field and a magnetic field. If you have a magnetic field, if you put a bar magnet on the counter in front of you and dump a bunch of iron filings around it, you'll see the iron filings start to take a series of bow-shaped shapes around the different poles of that magnet. And that's a way to visualize the magnetic field of that magnet. Now, if that magnetic field is to be perturbed and an oscillation is put into play, then you start to have magnetic waves. And anytime you have a magnetic wave, you have an accompanying electric field wave. And the reverse is true also. You cannot have a wave in an electric field or a magnetic field without the other. And that's why they're called electromagnetic waves. No kidding. Okay, so this is neat and interesting and stuff. But all of these electromagnetic waves, they're just different ways for energy to move in different mediums. And the different electromagnetic waves can be used for different purposes. And they start, as I mentioned, at extremely low frequency waves that are on the order of single-digit hertz, 1 hertz, 2 hertz, 3 hertz.
And with
so
those
forth.
ones, we're talking radio waves, right?
We're talking waves far below what your standard radio would be, and I'll talk about why in a minute.
Okay.
And they go all the way up to those gamma rays, which you sometimes find in high-end medical equipment, particularly cancer-treating medical equipment. But the other characteristic of waves that I want to talk about before I go into all of that is a parameter called wavelength. And the wavelength is related directly to the frequency. All of these electromagnetic waves travel at the speed of light. We talk about the speed of light, but we really mean the speed of electromagnetic wave propagation in vacuum. And that's 3 times 10 to the 8th meters per second, whatever. So given that they all move at the same speed, if they have different cycles, then you can figure out what the wavelength is based on the cycles, the frequency. And when I talk about wavelength, I mean the physical distance between 2 identical points in that wave, between 2 of the troughs, or between 2 of the peaks, or between 2 consecutive midlines, whatever. That's the wavelength. And so if you have a wave that goes through 3 complete cycles every second, that wave travels 3 times 10 to the 8th meters in that same second. That means that in that 3 times 10 to the 8th meters, you have 3 complete waves. What that really means is that each one of those waves is roughly 100,000 kilometers long. And when you get up to higher frequency things like the UHF that you used to find in old televisions, you're in the range where your waves are about 1 meter long because your frequency is much higher and each wave is shorter. And when you get up to the extremely, extremely high frequency waves, the gamma rays and so forth, you have wavelengths that are about the same physical length as the diameter of an atomic nucleus. They're measured in, I don't even know, picometers, I think. Yeah. So the wavelength and the frequency, these are just characteristics of these different waves. And what this means for you practically is that if you want to generate or receive or manipulate any of these waves, your antenna that you use to transmit or generate them has to relate to the wavelength at a certain level. If I want to generate a UHF wave, which has a 1 meter wavelength, then I need an antenna that's going to be around that order of magnitude. I can get away with a half meter antenna or a quarter meter antenna or a 1 meter antenna or whatever. But if I have a millimeter long antenna, it's going to be pretty difficult for me to pick up a UHF wave.
Basically, quantum physics is once you get down to small enough particles, you're dealing with different things. So all of classical physics kind of goes out the window. There's only a couple of things that hold, like conservation of momentum, conservation of energy. But once you get down to the atomic and subatomic scale of things, like really, really small particles, then your physics has to all change and things just don't work anymore. So they have to basically change the whole field to have just quantum physics as its own field. As you said, quantum also refers to discrete you quoted Latin as how much, but like
Right.
discrete steps. So part of the problem was that there are particles and there are certain like levels of energy that were being emitted that couldn't be explained why it was discrete steps of energy from certain atoms as like electrons fell down from levels within there. Yeah, a good example of quantized things would be stairs. You can't be halfway between a stair. You're either on one stair or the other. So within the realm of quantum physics that people understand, some people might think of the Bohr model of the atoms, where you have like electrons that orbit a nucleus, which isn't entirely accurate, but when the electrons, quote unquote, move from one orbital down to another or come closer to the nucleus, emit a certain frequency of electromagnetic radiation, which is discrete, and they are always in, or discrete as in a certain level. It's never like you might have a 1 or 2, but you'll never have 1.5, for example.
How does this discrete nature of quantum mechanics also work statistically?
Yeah, that's a really good question. This is something we're actually, from what we've talked about, we were going to talk about later in the podcast, but simply that particles are never, it's hard to tell exactly where they are, and if you know exactly where they are, you lose other information.
What is the Higgs boson?
The Higgs boson is something that was very exciting to people because it confirmed the standard model of particle physics, which is inherently complicated. It breaks up particles into quarks and leptons, and the Higgs boson was something that Peter Higgs hypothesized would exist, and they later did find that it existed. The reason they built CERN mainly was actually to find the Higgs boson. But basically, CERN, as Matt described, as a particle accelerator. They have these really long tubes that they levitate tiny particles in, and then they speed them up to the speed of light, basically, and ram them into each other. And when they do, they basically fracture these little particles into even smaller subatomic particles, which are things that they can study. And the Higgs boson was one of the tiny subatomic particles that they hadn't been able to prove existed. But if it did exist, it was something that would fit within what's called the standard model, which is, as we discussed, divided into quarks and leptons. And I don't know if we want to get into what those are, but they're basically what makes up even smaller particles. Like a proton, for example, is made up of quarks. So someone might say that you have a proton, which is one of the smallest particles there is, but you can break a proton up into even smaller particles, and those are called quarks. And they're, for example, an up and a down quark to make one proton. We discussed it a little bit, but the electron is actually a lepton. Leptons are all indivisible. You can't get any smaller than that, where quarks are also indivisible, but they make up things like protons and neutrons. So each quark has a certain charge to it. The up, charm, and top quarks have a 2/3 charge, and down, strange, and bottom have a negative 1/3 charge. And you can get to either a neutral charge, like a neutron, or a positive charge, like a proton, by adding different combinations of each of those. But they have really interesting
part of
names.
Yeah, it sounds like you're just saying random words at some point, but yeah,
I'm pretty sure
the
you made up
names
that
of
business.
the names of the quarks are, there's the 6 of them. What are they again?
There's up, charm, top, down, strange, and bottom.
Yeah.
As much as people might like to split a proton into the very smallest particles we can get, it would take infinite amounts of energy to ever do it, so we'll never be able to isolate an up quark or a strange quark or charm. Quantum field theories are very complex, but there are 4 fundamental forces within quantum physics and within all of physics, actually. But those are composed of electromagnetism forces, which are electricity and magnetic fields and forces. Those ones interact. They're not one and the same, like you have magnetic and electric forces, but They can also interact but you can have electricity and magnetism that can feed off of each other. I won't get into the details of that, but they're carried by a force. So each of these forces is carried by what's called a force carrying particle. So electromagnetism is carried by a photon and has an infinite range. So it can be infinitely far away. You can be infinitely far away from a charged particle, and you'll always be able to detect some force from it. In terms of strength, the strongest force is called, ironically, the strong force. And that's what binds quarks together that we were talking about with the weird names. The strong force is carried by what are called gluons, though. Don't ask me what those are or how they discovered them, because I don't know. But it's the shortest range force as well, which means that it basically can only be felt binding those quarks and, yeah, basically the quarks together within an atom or within a proton and neutron. And then you have the weak force, which is a really short range force, but it governs particle decay. And it's carried by bosons, which you may recognize. The Higgs boson is one of them. But other bosons that you have in the standard model are W, positive and negative W, and Z, and the photon and gluon are all bosons. And then the last fundamental force you have is gravity, which is carried by something called the graviton, which also created a bit of a wave in the news and physics recently. But they hadn't yet observed it till I think it was 2 years ago that they observed the first graviton.
Give us the layman take on wave-particle duality.
So this was, I believe, originally postulated by de Broglie, a physicist named de Broglie, which is an interesting name.
And it's spelled de Broglie.
Yep. Basically, though, it just means that everything is both a particle and a wave. So no matter the size, you are like every person, every planet, every solar system has some wave characteristics and some particle characteristics. So as you get down to much smaller particles, you are much more likely to exhibit higher wave characteristics. Another physicist that talked about this was Heisenberg, with Heisenberg's uncertainty principle. But in his, he described the ways in which we can tell how much particle and how much wave characteristics a certain thing might have. So the faster something moves, the more it acts like a wave, and the smaller something is, the more it acts like a wave. You can basically pick, if you want to know how fast or the momentum, those aren't entirely one and the same, but for simplicity's sake, you can pick how fast something is going if you want to know how fast it's going or where something is.
I mean, that essentially is the Heisenberg uncertainty principle. You can know where it is or where it's going, one or the other, not both. But yeah, is that related to the wave-particle duality directly? Could you elaborate on that, or is that a whole separate principle?
To some degree, if you don't know where something is, it's exhibiting some sort of wave characteristic that you don't know. Like, you know it's in some certain area. You might know that it's contained in a certain area, but you don't know exactly where it is. And you can pinpoint exactly where it is if you want to sacrifice all your certainty about its momentum or velocity to some degree. Another interesting thing with the Heisenberg uncertainty principle, the reason I hesitated to say momentum hesitated to say velocity is momentum is different and is always conserved even on quantum scales. So this is not usually a problem differentiating between velocity and momentum, because you can just add the mass or multiply the mass to your velocity and get your momentum. But once you start going at certain speeds, your mass actually can change as well. Schrodinger's cat was a thought experiment proposed by Schrodinger, who is a physicist, and he was honestly, it wasn't meant to be a serious thought experiment. It was meant to show how foolish it is to talk about these things on a macroscopic level rather than a quantum level. But he proposed it, and people took it more seriously than he might have wanted. But the idea is, in his thought experiment, was that there is a large box that has a cat inside of it, and there's also a Geiger counter and a bottle of acid, and there's a radioactive element within the box as well. And with radioactive elements, you never know when it's going to decay. You can tell in broad strokes like how often it'll decay with a ton of different decays and a ton of different particles. But if you just have a single isotope, you never know for certain exactly when it will happen. So in this thought experiment, the isotope is placed in the box with the cat, and if the isotope decays, then the Geiger counter will pick up that decay and break the bottle of acid and destroy the cat. And if it doesn't decay, then the cat is still alive. So he proposed trying to show how foolish it is to talk about these things in a macroscopic scale, that if you don't open the box, you don't know if the cat is alive or dead. So the cat is both alive and dead. That's kind of saying, like on a quantum scale, for example, you have uncertainty of where an electron is in the electron cloud of the atom. And on a quantum scale, the electron is in every position within that cloud that you can create using certain models. But because we don't know where it is in every position within that cloud, and we're just not certain as to exactly where it is at any given point. My understanding of quantum entanglement is pretty limited. I can give one example of something that is interesting, but it's basically that things might interact that we don't specifically understand, and the information travels faster than it should be able to. The speed limit of the universe is the speed of light, and there are certain particles that are linked to each other in some way that I don't understand, and I don't believe there's a lot of understanding yet on how they do interact. But there's a particle called a buckyball that you can split into two, and you can take them to vastly different locations. You could have one here and one on Pluto, and if you were to spin one, the other one would spin at the exact same instant without the delay of the time it would take for light to go between the two. So there's a lot of potential for this kind of knowledge to make a huge difference in space travel, because currently messages take forever to get between these two different locations, and it's hard to control, for example, a probe on the surface of Mars if you have to wait for like 5 minutes for it to actually react to the instructions you gave it. But if you could give instantaneous instructions, then it would make a huge difference in space travel and transferring information.
Trigonometry, from the Greek trigonon, meaning triangle, and metron, meaning measure. Okay, it's the study and science and math of triangles, how to solve a triangle and understand them, and so on and so forth. And when we talk about solving a triangle, we're going way back to the basics here. A triangle has 3 sides. Because of that, it also has 3 angles between the sides, thus the name triangle. So the thing is, yeah, we all know what a triangle is, but it turns out that in many cases in mathematics, science, engineering, astronomy, physics, trigonometry can either be required or make your life significantly easier. So when we talk about trigonometry, we're talking about solving triangles. And what I mean by solving triangles is finding the values of the sides or the angles or both. You find triangles all the time in your trigonometry textbook, but you also find them all the time in nature, in engineering, in the lab, in a number of applications. It turns out that those story problems that you love in your textbook are actually the only ones that matter, because they help you see the triangles in real life, and then when you encounter them, you know how to deal with them and solve them. So let's talk about what our objectives are. I kind of mentioned it. The objective of trigonometry is to help a person solve a triangle, to find the value of an unknown side, assuming that you have the values of the other sides or angles, or find the value of an unknown angle. If you, as long as you have parts of the triangle, trigonometry is the science of figuring out the other parts. And we use 6 basic trigonometric functions to do that. These are the sine, the cosine, the tangent, the secant, the cosecant, the cotangent. And if you didn't memorize those as I said them, that's okay. We'll go through them one by one and what they are and what they mean. So, Carl, let's say you have a triangle, as you often encounter in your daily life, and you know the length of 2 of the sides and the angle between the sides. Can you imagine that?
I can imagine that.
Yeah, imagine holding chopsticks in your hand, and the angle that the chopsticks make as they extend past your hand. You have the 2 sides and you have a specific angle. If you wanted to put another line connecting the ends of those 2 chopsticks, how long would that line need to be, and what angles would that line make with the 2 chopsticks that you have? Well, you can figure that out if you know what to do and how to use the trigonometric functions. The sine, the cosine, the tangent, the secant, the cosecant, and the cotangent are the things that you use to solve that. Let's talk about right triangles specifically. A right triangle is a specific type of triangle where one of the angles equals 90 degrees. Quick question. What is the total amount of degrees in the angles of a triangle? If you take the 3 angles and add them together, what number should you get?
Ooh, 180, 180.
Very good.
Wait, $1, Bob.
No, not dollars at all.
Sorry, I'm
Every
getting
triangle
myself
in the world, when you add all of the angles together, it comes to 180 degrees. A right triangle is a specific type of triangle where one of those 3 angles is 90 degrees. The other 2 angles, when you add them together, add to 90 degrees, and so you get 90 plus whatever equals 180. But right triangles are kind of the easy ones to use trigonometry on to solve for a missing side. And we'll use a right triangle to talk about the first 3 trigonometric functions, the sine, the cosine, and the tangent. What these are ratios. The sine, the cosine, and the tangent are ratios of one side of the triangle with another side of the triangle. The sine and the cosine are, and specifically when you have a right triangle, obviously you have 3 sides, but the longest of the 3 sides is called the hypotenuse. That's a fun word to say fast if you're the type of person that derives enjoyment from saying words fast. But the hypotenuse is the side that is opposite to the 90-degree angle. It is the side that the 90-degree angle does not connect to. So those 2 other sides that are not the hypotenuse, those are the 2 that come into play when we talk about the sine and the cosine, because the sine and the cosine are the ratios of one of those 2 smaller sides to the hypotenuse. And so we'll start with the sine. If I have a triangle and a right triangle, and I know right off the bat one of my angles, right?
Right, 90 degrees.
Yes, because it's a right triangle. Let's say that I know one of the other angles. Only one. And let's say that I know the length of the hypotenuse. So I have one side, I have the hypotenuse, and I have the right triangle, and I have one of the other two angles. That's fine. Let's say that that other angle is 60 degrees. Now, if I know I have a right triangle, and I know one of the other angles, my 60-degree angle, do I know automatically what the third angle is?
You do.
Yeah, I totally do. It's whatever I need to add to 60 to make 90. Happens to be 30. So if I had a 90-degree angle for my right triangle, and then my second angle was 35 degrees, I would expect that the other angle would be 55 degrees. So going back to our right triangle, imagine, if you will, you have your 90-degree angle. Say it's at the bottom left. Imagine you have the 60-degree angle. Say that that is at the bottom right. And imagine you have your 30-degree angle. It is at the upper left. Now, I know the hypotenuse. It goes from my 30-degree angle to my 60-degree angle. And let's say that it is 1, because that's a fun number. Now, what if I want to...
It's the loneliest number.
I'm
sorry. Go ahead.
It's... we're in different time zones. I'm not able to adapt as quickly as Carl is here. All right, that's fine. So let's say I want to solve for the other two sides of that triangle. Well, because I know the length of my hypotenuse, I know that it's 1. Because I know my other angles, 30 degrees and 60 degrees, and because I know what a sine is, because I listened to this podcast, I can figure that out. Okay, well, let's solve first for the length of the side that does not touch the 60-degree angle. It's the side that goes from my 90-degree angle to my 30-degree angle. To do that, I'm going to use the sine function, or the sine is of an angle is a ratio. And every angle in the world has a known sine and a known cosine and a known tangent and all of these things. These values are known. And if I know the angle, I know the ratio of those sides, and I can use that to very quickly solve for my unknown side. So let's go back to this. The sine of any given angle is the ratio of the opposite over the hypotenuse. I mentioned I know my hypotenuse. My hypotenuse is 1, because that's easy. The sine of my 60-degree angle then will tell me the number that if I divide that number by 1, I will get the length of that other side. Okay, what does that mean? Sine of 60 degrees. Sine of 60 degrees, the actual value is 0.866. What that means is that the opposite side, my unknown side, if I divide that number by 1, I should get 0.866. Well, now I have a simple algebra equation that I can solve, and I made it really easy because I said my hypotenuse is 1. 0.866 equals x divided by 1. X, therefore, must be 0.866. The opposite side from that 60-degree angle is a length of 0.866. And I just figured that out. Now, the ratio holds true no matter what the length of my hypotenuse is. What if my hypotenuse was 10? Well, then my equation would be that the opposite over the hypotenuse still equals 0.866. So I have some number, the opposite of some length. That number over 10 equals 0.866. Well, solving that very simple algebraic equation, I get that my unknown number is simply 10 times 0.866. It's 8.66. And I can very quickly solve for my unknown side using that sine ratio. Well, that's neat. I figured out the length of the opposite side. Now, what if I want to solve for the length of the side that does touch my 60-degree angle? The one that is not the hypotenuse, but the one that connects my 60-degree angle to my 90-degree angle. That side is called the adjacent. Adjacent because it touches the angle in question. My opposite side does not touch the 60-degree angle. The adjacent side does. Well, to solve for the adjacent, I use a different ratio. I use the sine. The sine is defined as the ratio of the adjacent over the hypotenuse. Okay, so what's the cosine of 60 degrees? And it turns out it's 1/2. I do the same algebraic equation. My unknown length divided by my hypotenuse equals 1/2. Doing some quick algebra, I learned that my unknown length equals 1/2 times the hypotenuse. If my hypotenuse is of length 1, then my adjacent side will be 1/2. If my hypotenuse is 10, then my adjacent will be half of that. It will be 5. And using those two ratios, I can very quickly solve for the unknown sides of my right triangle, which is neat. I can do all these things as long as I know the hypotenuse. What if I don't know the hypotenuse? Then what do I do, Tim?
That seems
You
about right
call
for Tim.
an expert.
You call an expert, yes, or you listen to this podcast.
That's right.
Well, I know my angles, and let's say that I know the other two sides, but I don't know my hypotenuse. In fact, I don't even need to know both of my other two sides. Let's say I just know
Don't you just
one.
need to know one side and two
Yep.
angles?
Yeah. Well, and in a right triangle, it's pretty easy. If you know
Right.
two angles, you know three angles.
Yeah, right.
Because right triangle. But yeah, all I need is to know one of the sides in a right triangle. If it's not the hypotenuse, though, can I use the sine or the cosine? Well, not yet. First, I have to figure out what the hypotenuse is, and to do that, I have to figure out what the other two sides are. And this is where the third trigonometric function comes into play, the tangent. The tangent is defined as the ratio of the length of the opposite side over the adjacent side. So let's go back to my 30, 60, 90 degree triangle, and specifically, let's go back to my 60-degree angle. Let's say I don't know the hypotenuse, but I do know the length of the, which one do you want? The opposite side or the adjacent side, Carl?
Adjacent.
I know the length of the adjacent side. I also know that I have a 60-degree angle, and because I know that, I can use the tangent function. The tangent of 60 degrees is 1.732. I didn't make this up. That's just what it is. And using that, I know that the opposite side over my adjacent, which Carl told me I know. What's the length of my adjacent, Carl?
10.
10. It's 10. Okay. I know that the opposite side over 10 equals 1.732. 05081. Well, anyway, that's fine. Again, doing a very quick algebraic equation. My unknown over 10 equals 1.732. That means my unknown equals 10 times 1.732. My unknown equals 17.32. And I just figured out the length of that unknown opposite side. Now, at this point, I know two sides of the triangle, don't I?
Yes.
Yes. Can I very quickly figure out the length of the other side?
You can.
Yeah, I can. And I can do it by going back to a sine or a cosine function. And in fact,
It's
once
probably
I had
also
the
a good
opposite
time
or the
to.
adjacent, I could have used the sine or the cosine function earlier. But anyway, sorry. Go ahead, Carl.
I was going to say this might be a good time. I don't know if you do this later, but to kind of give it a real world example. where this might be useful beyond a trigonometry class or what some other, geometric class, engineering class you might be in the real world. Let's say you want to know the height of a building or the height of a specific lamp post or something which you can't like just climb up and measure. This is where you could use something like this, right? You can essentially create a right triangle in a 90-degree angle from the base, walk out a certain specific distance so that you then know one side of the triangle, and then you just if you can get the angle from where you're at to the top of the object that you're trying to measure, then you've got your triangle set up and you can solve.
Yeah, the classic example is find the height of a flagpole using its shadow.
Right.
Well, assuming the ground is flat, the shadow and the flagpole will form a 90-degree angle, so you have a 90-degree triangle. If you walk to the tip of the shadow and you use a protractor or compass or something to measure the angle between the tip of the shadow and the tip of the flagpole up in the air, you've now figured out a second angle. You've got your 90-degree angle at the base of the flagpole, and you've got whatever it is that you measured, say it's 60 degrees from the tip of the shadow to the tip of the flagpole. You can measure the length of the shadow, and then using the trigonometric functions, you can figure out how tall the flagpole is. So in the case of that flagpole shadow example, if I'm standing at the tip of the shadow and I'm at that angle point looking at the top of the flagpole, the shadow is going to be my opposite or my adjacent?
The shadow's going to be adjacent.
Yes, because it's connected to me.
Yes.
The flagpole itself is going to be the opposite because it's not touching me at all. And an invisible line running from the tip of the shadow to the tip of the flagpole would be the hypotenuse. Now, the easiest way to solve for the height of the flagpole would be to use the tangent function. If I'm there and I'm measuring a 60-degree angle between the tip of the shadow and the tip of the flagpole, then I know that the length of the flagpole, the opposite, divided by the length of my shadow, the adjacent, is equal to the tangent of 60 degrees, which happens to be 1.73. How long was my shadow, Carl? 5 feet, 10 feet, 150 feet?
10 feet?
It was 10 feet, let's say.
Yes.
So I measured my shadow to be 10 feet. I know that the opposite divided by 10 has to equal 1.732. Doing some algebra, the opposite, the length of the flagpole, equals 1.732 times 10. Therefore, the length of the flagpole is 17.32. If I measured a 60-degree angle. If I measured a 30-degree angle, well, what's the tangent of 30 degrees? It's a different number. It's 0.557. If I'm still measuring a 10-foot shadow, that means that my flagpole is 5.7 feet tall. That's a pretty lame flagpole. But anyway, that's a quick way that you can measure that you might find a practical use for a trigonometric ratio in your day-to-day life as a city flagpole measurer. Let's talk about another property of right triangles, and this is a little bit more geometry than trigonometry, but it's still important. Have you heard of the Pythagorean theorem? Well, if you're listening to this podcast, we will assume no. But the Pythagorean theorem is a way to determine any of the lengths of a right triangle, assuming that you know the other two lengths of the right triangle, and you don't even need to know the angles at all. That can be a complete mystery to you. But the Pythagorean theorem basically states that the two non-hypotenuse sides, the opposite and the adjacent from whatever point, basically whichever sides are not the hypotenuse, if you take those two sides call them A and B. If you square A, you take A times A, and you take side B and you square that, B times B, and you add the two together, so A squared plus B squared, well, it turns out that that is equal to the hypotenuse squared. Call the hypotenuse C, and your Pythagorean theorem reads out as A squared plus B squared equals C squared. So let's say that I have a, let's go back to our little flagpole example. For some reason, I know the height of my flagpole. I've measured it and it's 10 feet tall. I've also measured the length of the shadow, and it's 5 feet tall, or 5 feet long, rather. Apologies. For some reason, I am now obsessed with knowing the length between the tip of the flagpole and the tip of its shadow. That length being the hypotenuse. That would be C squared. I'm sorry, that would be C, not C squared. Well, because I know the Pythagorean theorem, I can now figure out what the length is between the tip of the shadow and the tip of the flagpole. My flagpole is 10 feet tall. That's A. I'm going to square that. 10 times 10 is 100. The length of the shadow is B. That's 5 feet. I'm going to square that. 5 times 5, that's 25. I'm now going to add the two together. So I get 100 plus 25, and I have 125. That number is equal to the length between the tip of the flagpole and the tip of its shadow squared. And so if I take the square root of that number, then I can get the length, that length, the length between the tip of the flagpole and the tip of its shadow. So I take the square root of 125, and it's kind of a messy number. It's 11.18. But that way I can very quickly figure out what the hypotenuse of any given right triangle is. Now this works if I don't know one of the other sides, but I do know the hypotenuse. If I know the hypotenuse, I know what C is, and I know one of the other sides, well then doing some algebra, I can very quickly solve for that missing quantity. But that's kind of a property of triangles, of right triangles specifically. If I don't have a right triangle, then I have to do some other fun stuff that we'll get to in a minute when we talk about the law of sines and the law of cosines. But let's talk about the three remaining trigonometric functions. We talked about the sine, the cosine, and the tangent. Those are the first three. Again, the sine is the ratio of the opposite side divided by the hypotenuse. The cosine is the adjacent divided by the hypotenuse. And the tangent is the opposite divided by the adjacent. Okay, so the other three trigonometric functions relate to the first three that we talked about, the sine, the cosine, and the tangent. The other three trigonometric functions are in order: the cosecant, the secant, and the cotangent. The cosecant is, well, and the secant and the cotangent are respectively the inverses of the sine, the cosine, and the tangent. What does that mean? Well, if the sine of an angle is the opposite over the hypotenuse, the cosecant is the inverse of that. It's the hypotenuse over the opposite. It's a way to make the math a little bit easier if you know, depending on which side you know. If you know the hypotenuse or you know the opposite, it's a little bit algebraically easier to use the sine or the cosecant, depending on which one you know. Okay, great. The others are the same way. The cosine is the adjacent over the hypotenuse. The secant is the inverse of the cosine. It's the hypotenuse over the adjacent. The tangent is the opposite over the adjacent. The cotangent is the adjacent over the opposite. They're connected trigonometric functions, and you can use them to solve virtually any triangle in existence if you use them appropriately. Now, let's say though, I said any triangle in existence, and all I've talked about is right triangles. Well, what if I don't have a right triangle? What if I have a messy, gross triangle that doesn't have a 90-degree angle anywhere inside it? Then what?
Give up.
No, you turn into this podcast so you can figure out what to do.
Right, that's why I'm here.
Yes. Using these ratios, though, which hold true for any triangle out there, you can still find your unknown values, your unknown angles, and your unknown sides. And if you don't have a right triangle, well, then you might end up having to use something called the law of sines or the law of cosines. The law of sines is actually pretty simple. For any triangle in existence, the three trigonometric ratios the sines of the three angles in that triangle and the ratios that those sines represent, they're all going to be related. Now, what if I have a triangle and I've named the angles A, B, and C, as I do? The law of sines says that the length of the side that is opposite my angle divided by the sine of that angle is equal to the length of some other side divided by the sine of the angle that is opposite to that side. Okay, that's very hard to give someone a clear picture of verbally, but I'm going to try anyway. Imagine my flagpole example. All right, now that's a right triangle, so imagine that the flagpole just survived an earthquake or a hurricane and is now tilted over a little bit. So it's not making a 90-degree angle with the ground. It's still sticking up in the air, but it's at some skewed, slanted angle. It's casting a shadow, and that's going to be on the ground, and there's going to be some length, say a piece of rope that you've tied to the top of that flagpole, and you've driven it into a stake into the ground at the tip of its shadow. You now have a triangle. There's not a 90-degree angle anywhere on it, but it's there. Now, we're going to say that the angle at the top of that flagpole is angle A. What side is going to be opposite to A? Well, it's going to be the shadow that's on the ground. That shadow does not touch angle A. Now, let's say that the angle where the flagpole sticks into the ground is angle B. Well, what side is going to be opposite B? It's not going to be the flagpole itself, and it's not going to be the shadow. Those both touch B. The opposite is going to be that string that you ran from the top of the flagpole to the end of the shadow. That's going to be side B, opposite angle B. And then finally, angle C is going to be the angle where you've plunked that string into the ground at the tip of the shadow. And side C, opposite angle C, is going to be the flagpole itself. Okay, going back to the law of sines. The length of the shadow is A, and the angle at the top of that flagpole, between the flagpole and the string, is angle A. The law of sines says that the length of the shadow divided by the sine of angle A is some number. I don't know what it is, but it's some number. Now, that number will be the exact same as side B divided by angle, or divided by the sine of angle B. Side B was that string, and angle B was that skewed angle between the flagpole and the ground. If I take the length of that string and I divide it by the sine of B, I will get the same number as if I had taken side A, the shadow, and divided it by the sine of angle A at the top of the flagpole. Likewise, if I take the length of the flagpole itself, C, and divide it by the sine of angle C, the angle between the shadow tip and the tip of the flagpole, I will get that exact same number. And so this gives me a powerful algebraic equivalency where if I know 3 of those things, I can solve for the 4th one. If I know 2 angles and a side, then I can solve for the unknown side. If I know 2 sides and an angle, I can solve for an unknown angle. But that's the law of sines. That allows you to solve unknown sides and unknown angles, and that law is universally true for all triangles, not just right triangles. The law of cosines is a little bit more complex, and I don't want to go into it because it's even harder to verbalize without drawing it out. But I will. I'll state it anyway. It's another algebraic equation that tells you how things relate to each other. And if you know parts of this equation, then you can solve for an unknown part. The law of cosines basically says that the length of side C squared, that's going to be whatever's opposite angle C, the length of C squared equals length A squared plus length B squared minus 2 times length A times length B times the cosine of the angle at C. I'm not going to try to illustrate that one, but if you have questions on it, look it up, and you don't have to memorize it. The internet was built so that we didn't have to memorize these things. But using this equation, if I have angle C and I have side A and B, I can now solve for the side at C. That cosine law applies to all of the sides and all of the angles. It's not just C squared equals A squared plus B squared minus 2AB cosine C. It's also A squared equals B squared plus C squared plus blah, blah, and B squared equals A squared plus C squared minus 2AC cosine B. It works for all of the sides and all of the angles. So if I know 2 of my sides and I know 1 of my angles, the other angle, then I can use the law of cosines to figure that out. Now, when would I use the law of cosines versus the law of sines? I didn't really explain that, and I should. Basically, you use the law of cosines when you know 2 of the sides and you know the angle that is between the 2 sides. That's basically, you would know side A and B and angle C. The law of cosines doesn't help me if I know A and B and angle A or angle B. The law of cosines only works if I know A and B and angle C, or if I know A and C and angle B. Basically, I have to know the angle that is between my 2 sides. Now, if I don't have that situation, then I can use the law of sines. The law of sines is the one I use when I know either 2 angles plus 1 of their opposite sides, or I know 2 sides plus 1 of their opposite angles. If I know angle A and side A, and I know side B, then I can use the law of sines to find angle B. If I know angle A and side A, and I know angle B, then I can find side B. and then I use the law of sines for that. However, if I'm in a case where I know side A and B and angle C, then I have to use the law of cosines. You select the law that you use based on the information that you know and the information that you don't know. Again, much easier to understand visually, but I hope that we're able to give you some kind of understanding of this one. There's a quick Google search of the law of cosines illustrated. The images will kind of graphically show you what you have available in terms of how to find an unknown based on what you do know. We have built laser, which, as you mentioned, stands for light amplification by stimulated emission of radiation. So let's talk about what that means and how a laser actually works. When we talk about light amplification, we're talking about making light brighter, more intense, more powerful, more bigger. And the mechanism that we use to do that is this stimulated emission, which means emission driven by some other source that causes that light amplification. And when we say of radiation, of course, we mean of light, of electromagnetic radiation. And you can find lasers that are, most people are familiar with visible light lasers because they produce a visible laser beam, a beam that you can see. But you have lasers that operate in all portions of the electromagnetic spectrum. You have infrared lasers, you have ultraviolet lasers, you have X-ray lasers. Theoretically, you should be able to build a gamma ray laser, although that one is difficult. But all of these are radiation, electromagnetic radiation, and it's all artificially, or rather externally stimulated, and it all results in the amplification of that radiation, generally visible light. So how a laser generally works is you have something called a gain medium. This is the thing that you use to amplify your light, and your gain medium can be any number of things. It can be a gas, it can be a solid, it can be a liquid, it can be a plasma, it can be whatever. And different gain media will give you different types of lasers. And with that, you have your external source of power that you hook up to it, your external source of stimulation, I guess. And typically it's something like a basic light or an electrical current, something like that. But what you do is you move energy from that external source into your gain medium, and through the wonders of laserness, that gain medium will end up spitting out a whole bunch of photons, little bits of light, little light packets. And those photons will be all aligned with each other. They'll all be at the same frequency. They'll all be in the same orientation or polarization. They'll all be within phase, or rather with a constant phase relationship to each other. That's a technical term that you don't need to worry about. The big thing is you'll end up having a bunch of photons that are what we term coherent. They match each other in terms of the light that they represent. At that point, you can focus it, you can align all of that light together so it's all going in the same direction, and that results in a laser beam. And we'll talk about all of the different parts of that. But let's go back into that stimulated emission. I glossed over it with the term through the magic of laserness. Well, that magic is actually, that's the key of what makes a laser a laser. within your gain medium, your gain medium being generally made of some sort of physical matter rather than wishes and dreams, it will have atoms. And those atoms will have a nucleus and a bunch of electrons floating around them, and so on and so forth, as all matter does. Well, depending on the gain medium you have selected, those electrons zipping around those atoms will be in different energy states. And you can select a medium that is very susceptible to receiving additional energy and moving those electrons from one state to another. And that change in energy state, all of that will come with a very specific amount of energy required to affect that change. For example, a ruby crystal. Again, a ruby is a physical object, therefore it is made of atoms. Those atoms have nuclei and electrons. Those electrons within that ruby crystal will absorb very specific energy levels that will move the electrons from a low state to a highly excited state. And that amount of energy, whatever it is, when that gets pumped into that ruby crystal, you'll see those bits of energy absorbed. And then, because of the way atoms work, you'll get those electrons excited to that higher state, and then they will very soon start to decay back to that lower state. And here's where the magic of laserness comes in. When the electrons in those ruby crystal atoms decay from their highly excited state to their non-excited state, they change energy, they drop energy. And because energy cannot be created nor destroyed, the atom has to give up something to have that energy drop happen. And the something that it gives up is a photon of light. And it chucks that light off into the void within that ruby crystal. Now here's where the magic happens. That newly emitted photon is that chunk of light is at a frequency that is dictated by the energy change needed to raise that electron from one level to another. And in a ruby crystal, that wavelength of light that corresponds to that energy bit happens to be red. And so it will emit a red photon. And as that red photon travels throughout the remainder of that ruby crystal, it will pass other excited ruby atoms. And as it passes them, because of the deep magic that I will freely admit I don't fully understand, but as it passes those other excited ruby atoms, it will stimulate them, there's that key word, to release their own photons, which will again perfectly match that energy level. They will be red. And because photons are super creepy, they all like to be exactly like each other. So if I have one atom, if I have two atoms next to each other, A and B, they both have an excited electron. A releases a photon first, and the photon passes atom B. It stimulates atom B to drop its own photon. When that happens, both photons from A and B will release its photon to perfectly match the photon from A in both phase and wavelength and everything else and direction.
Is this like some of that quantum physics creepy weirdness?
Yeah, this is the deep magic.
Okay.
But that's the key. They will match in direction as well. And so and as those two photons start zipping through that crystal, well, they're going to pass other atoms, stimulate them to drop their own photons, and suddenly you have a whole horde of photons of red light all moving in the same direction. And that's how you get that light amplification by stimulated emission. You put a bunch of energy into this crystal, that energy will raise the electron levels of some of those atoms. Those atoms will start to release photons of red light, and those photons will in turn trigger the release of additional photons that will match in amplitude and frequency and direction, and they will become coherent. And very quickly, you get coherent light zipping around inside this crystal. Well, that's cool. If I really want to make a glow-in-the-dark ruby nightlight, that's how you do it. Great. The way that you get a functional laser out of it is to shape that thing into a cylinder and coat both ends with a mirrored surface. And what you would have then is the core to your laser. All of that light that is now zipping around inside that crystal, that coherent light, some of it's going to bleed out the cylindrical surfaces, the curved surfaces of that cylinder. But any of the light that's going out the ends is now going to start hitting those mirrors. And it's going to bounce back and forth between those mirrors, trapped in there, continuously amplifying the light levels inside that ruby. And suddenly you're going to have, just like your speaker is and your microphone are continuously looping an audio signal until it's unbearably strong. So very quickly you're going to get streams of coherent light bouncing from one end of this ruby cylinder to the other and amplifying themselves by triggering the release of additional photons from excited ruby atoms, and suddenly you're going to have phenomenal amounts of light all heading in the same direction, feeding itself by triggering the release of even more light within inside that crystal. And that's great if you want to just pump a ruby crystal up so full of light that it eventually melts, I guess. I don't know. So how do you get a beam out of that?
Is that a rhetorical question?
That's the question for the day. That's the question that you had to solve. You've now basically got light trapped inside this ruby. Well, that's neat. What do you do to get it out?
I have an idea.
Yes, Johnny.
I have no idea if this is right, but what if you had, so you have the mirrors on both sides of the cylinder.
Yep.
But what if one of the mirrors had a small opening, so it reflected most of the light but allowed some of it to pass out? And
so turns out that is exactly what you do.
Sweet.
Put a little pinhole in the center.
That's why they paid Johnny the big bucks.
Yep. You put a pinhole in the center of one of the mirrors, and that's your laser beam. And there you go. The other thing that you can do is you can make one of the mirrors perfectly reflective, and you can make the other mirror 90% reflective. But what it really comes down to is that the fundamentals of physics, those are the underpinnings of all the inventions that we have. And when you truly understand those physical fundamentals and how to apply and manipulate them, well, you can do all kinds of fun things.